Thanks, everyone. So it's great to be here. So I'm going to talk about models interpretability. So there was this question in the title of the presentation, can you trust neural networks? So how many of you think that you can trust neural networks? Can you raise a hand? And not so much, so maybe my presentation is not so important, actually. So I'm machine learning tech lead at NetGuru. And we are building very quickly a new team, and we are doing computer vision, NLP, and some recommender systems, and a lot of stuff, actually. And if you're more interested, you can catch me later. Yeah, and so let's move on to the topic of the presentation. So I would like to start with a question. Let's imagine that you have opportunity to go to the AI doctor, who is 80% accurate and can explain its diagnosis, or AI doctor who is 90% accurate but cannot. So which one do you pick? So if you could raise the hand for the first one, for 80% with explanation. Okay, and for the second? Yeah, so I guess most of people believe in explanations. So that's great. So short agenda. So the first thing is motivation, why explaining neural networks predictions or any other model predictions are important. And then I'm going to talk about LIME and SHAP. Those are two frameworks for explaining machine learning models. So let's start with Zbyszek, who is going to a bank to get a loan. And there is machine learning model, which is deciding whether Zbyszek can get a loan. And machine learning models claims that there is 55% that Zbyszek is not going to be able to pay the loan. And he's got declined. And Zbyszek asks why. It's important for him to understand this, and it's important for his customer satisfaction. But also banks want to know why. Because, like the model might be wrong and it's about the profit of the bank, but the customer satisfaction is also important for the bank. So they're going to the data scientist, and data scientist says deep learning, AI magic. Yeah, so that's the common issue with models like neural networks or complex decision trees like XGBoost, that the complex models tend to be accurate, but tend to be at the same time not easily interpretable, while the simple models are interpretable, but not always have the same level of accuracy as the complex models. And you can see the trade-off between the customer satisfaction, in this case, like model interpretability, and the profits for the bank, like accuracy of actually predicting whether Zbyszek is going to be able to pay the loan or not. And the next motivation is actually from my life, why actually I'm interested in explaining machine learning models predictions. So for last 3 years, I worked on street-to-shop image search engine. So on the input, we had some image, like with some actresses or just from some shops, and the output should be the exact clothing items or similar ones. And the part of this whole system was a shoe kind classifier. So we were predicting soccer shoes, boots, high heels, ballerinas, and some other kinds. And our training procedure was quite common, quite standard. We split our data set into the training set, validation, and test set. There were 16 classes of those shoes kinds. And we had 10,000 images per class, which is quite okay. We measured performance with accuracy because the data set was balanced. And we did transfer learning of ResNet 50 in Café at the time. And we got accuracy like 93%. So can we trust this number? And I can imagine after your first responses that probably you wouldn't be so sure. And yeah, let's see a couple of predictions. So we have soccer shoes and we have high heels, and it works. We have some boots and sneakers. And then we have some predictions on high heels soccer shoes and on sneakers, I guess, still soccer shoes. So what's wrong here? So what do you think? What's wrong with this classifier? Do you have any ideas? Right. Yeah, so exactly. If we visualize the parts of the image that were crucial to decide whether it's high heel or soccer shoes, it occurred that the classifier looked at the grass. So how can we gain trust in machine learning models? So the first thing is accuracy and other metrics like precision, recall, or F1 score. But actually, if we have the different test data distribution, the training data distribution, which is not always very easy to check, it might lie to us. So the other thing is A/B testing model on production, but it's expensive, and we may expose the user to the poorly performing model. The next thing is obviously experience. If we have very experienced machine learning engineers, they probably can catch those things quicker than later. But at the end, there is interpretability. So actually understanding why our model is doing such predictions. So how do we define, what do I mean by interpretability here? So in this talk, I'm talking only about local interpretability, so on the level of single example explanation, which means that for a given input example and output prediction, we assign some importance score to the part of the input. And what are good explanation traits? So the first is it should be somehow aligned to human intuition. So like in this case of the grass, if the explanation would be correct and aligned to human intuition, then we probably should have visualized some parts of high heels, and especially probably heel. The other thing, it should be faithful to original model. It means that the model which is explaining the complex model for a given input should have the same prediction as a complex model. And the other thing would be great if we have some model for explaining which is model agnostic and can explain decision trees, SVMs, and neural networks, and any other model. And it might be difficult, but actually there are already a couple of frameworks which are tackling this problem. So let's talk about the first one. And it's called LIME, which stands for Local Interpretable Model Agnostic Explanations. And LIME has two key ideas. So let's imagine a classification case with just two classes. And we have some complex model that is doing predictions on this data set. And we pick a simple model, which is interpretable by humans, like linear model. And we do the prediction with this linear model for a given specific case. And this linear model locally is very good. You can see that we have good decision boundary for this green example, but this decision boundary would be very poor in other places of this area. So how does LIME actually work? So we sample data points which are close to the input example by some perturbations to the input example, and soon we'll see how it exactly works on images. But let's just imagine that we sample some data points which are close in some metric. Then we use this complex model to generate predictions for all those points. Those sampled data points, wrong way, are weighted by some distance to the input. And then we train simple model, like linear regression, on those weighted samples to predict some feature importance values. So they are basically the weights of linear regression. So on the particular example of images, so we have this input image on the left, and we do super pixel segmentation with quick shift algorithm. And then to generate close to the input image samples, we do perturbations by randomly covering some superpixels. And those are our training examples. And we do the prediction for a given label with this complex model. So the given label here is Labrador. And on those perturbated examples, we train linear regression. And exactly in LIME case, it's K-laser regression, which shrinks which shrinks parameters of the regression to 0 if the features are not important for for a prediction. And at the end, we can visualize only those superpixels which has high value of the weights of linear regression. So we can see that the most important part of this input image to predict Labrador was actually this dog face, and for some reason, some part on the bottom. So you can see that's not perfect. Yeah. So from the mathematical standpoint, Lime tries to minimize some loss function over a class of interpretable models G. So those are, let's say, linear models, and uses a kernel for weighting samples, which is this distance kernel. And Lime has some heuristic to choose this kernel, which is exponential function. And we have also this parameter of regularization. So you can imagine that this kernel, which is just chose by hand, probably it's not perfect. And we can smoothly go to SHAP, which allows us to choose better this kernel. So if we take the step back, in general, Lime is, we have some data, and Lime is working like we toggling some parts of the data. So in this case, we toggled x1 off, and we do the prediction, and we observe change in the prediction. And we can also toggle a subset of the features, and we can observe the change in the prediction. And observing those changes, we would like to somehow summarize the effect of changes on the prediction. And we summarize this computing feature importance values that we attribute to the model. So basically we have some features on the input, and our converted input are just ones and zeros that are stating whether some input is on or off. So we can replace this model with simple with just some of those feature importance attributes. And actually Lime can be expressed in this way also. And here is interesting connection to the game theory. So in 1953, there was some, let's say, discovery, or the first paper published on Shapley values. And actually, there is only one way to assign those feature important values if we assume three properties for this function. And those properties are local accuracy. So this means that the model is faithful to the complex model. So basically, for a given input and converted input to ones and zeros, we have the same prediction. The second one is missingness. So if some feature is missing, then there is no impact on prediction. And consistency. And consistency means that if we have two models and we compare those two models, and if some feature makes a bigger difference than toggling the feature in the second model, then importance of this feature in the first model has to be higher than in the second one. So we have those three simple properties, and then there is only one solution to obtain the feature important values for, in general. So how do we compute those Shapley additive values, also called Shapley additive explanations? So let's get back to the Zbyszek case, Zbyszek getting a loan. So there was 55% chance that Zbyszek is not going to get a loan and not going to pay the loan, so he's going to be declined. And we start with expected value on our prediction of complex model, and it's 20%, let's say. And how can we get to the risk for Zbyszek? So first we start with this base rate, 20%, and we condition this on some first feature, which is age. So Zbyszek is very young, so it increases the risk up to 35%. And the other thing, Zbyszek is day trader, so his job is not stable, and increase the risk further up to 70%. And we can go with all the features this way. So the next thing is how many open accounts Zbyszek has, and that he's married. So maybe he's not, maybe he's partying less, and maybe he's more working or whatever. And at the end, we end up with 55%. But the important thing is the order matters here, because you know, like the importance of day trader is quite high, because we already know that he is young, and maybe the young day trader is someone who is not stable in terms of his budget. And if we don't know that he's young, then it could happen that day trader feature importance might be lower. So to obtain actually the feature values for those sharp feature values, we need to average over all possible configurations. So there's n factorial possible configurations. It's not really feasible. And we can, so the idea is to do some approximations here. And here the lime comes actually. So we can connect the lime with sharp, and actually if we force local accuracy and consistency, there is a proof that we can compute the loss function, the regularizer, and the kernel for a lime directly, and we can use just lime to obtain Shapley values. So why actually this whole thing about Shapley values, that we can, if we can just use lime, why those Shapley values are important? And the main reason behind this is actually that Shapley values empirically, it's proven empirically, so it's not really proven theoretically, but it is observed empirically that Shapley values improve consistency with human intuition. So let's take Zbyszek again, and we have some data like whether he has a cough or fever or congestion, and we have some treatment model for some medication that works well on the early stage of disease, and it's not so important later. And the model outputs treatment priority for Zbyszek. So we have those rules that if we have cough or fever, then the priority is 5. If we have both, there is 2. Otherwise, it's 0. And let's say Zbyszek has both cough and fever, so the treatment priority by the model is 2. And we are interested what's the feature importance for cough and what's the feature importance for fever. So we can do those explanations with lime, and we can do those explanations with Shapley. But to compare with human intuition, we actually need to go to Amazon Mechanical Turk, prepare some tasks for humans, and let humans decide what's the influence of those features. And the authors of the paper actually did those kind of experiment, and they achieved some feature importance values that were stated by humans, and actually the feature importance values which were generated by SHAP were very similar, and by lime were quite much different. So this is the reasoning behind using actually SHAP in combination with lime. The other important things, we can actually define a lot of models that are trying to explain neural networks or decision trees, the models like deep lift or relevance propagation, in the same manner like Shapley values. So Shapley values are actually a unifying framework for those models. So I have this question again: which doctor would you choose? So already a lot of people chose at the beginning the model with explanation, but let's see whether it changed. So who would choose the 90% accurate without explanation? So I guess it's still it's even less than in the beginning. So the question comes actually from the Twitter, from the Pedro Dominguez, who wrote the Master Algorithm book, and he actually stated this question, and he said that he would choose the 90% because he doesn't care about explanation if he's going to die. Yeah, I would do the same, I guess. But I believe that explanations are very important to actually improve machine learning models, not necessarily to explain to the end user, but it's also important. It's also important from the legal issues, especially since GDPR. The other thing about the explanations, I don't know if you heard, but probably you heard about the Netflix price, and Netflix uses recommender system for the movies. And actually, the complex model, which wasn't explainable, performed for Netflix worse than the model which was explainable, and users of the Netflix could see actual explanations why those particular movies are suggested to them. So I would like to finish with the quote from Richard Feynman, that if you cannot explain something in simple terms, you just don't understand it. As also somehow motivation behind working in this specific area of machine learning, which is, I think those explanations are very young, but it's rising field. So I have some credits to the authors of papers and all the materials I used to prepare the presentation. And that's all from me, and thanks a lot.
Thank you so much, Mateusz. We have time for a few questions, I think.
Thanks for. I actually enjoyed the presentation, enjoyed it a lot. But I have some questions regarding Shapley values. I have noticed that some phenomena in Lime, for example, when let's imagine a simple case. You are trying to explain the decision tree or the ensemble of trees, and you try to explain something that's beyond the borders of your training set. So it kind of plateaus over there. And when you extract an explanation, it gives you all zeros. And it's supposed to, because there is no variation locally. Does Shapley deal with this? Because you need to reinterpret how you deal with explanations, with machine learning explanations in this case. So the question is, how does Shapley deal with things beyond the range of your known data?
Yeah, honestly, I think it doesn't deal with it, but I'm not sure.
Okay, one more?
Hi, thank you for the very nice talk. I have one question and one comment. The question is, how is this different from, let's say, random forest classifier or some other kind of ensemble methods? The whole thing about using a simplified model and then averaging over multiple ones of them and optimizing that. So that's the question. And the comment is about the last slide about Feynman's quote. And if you can't explain something in simple terms, you don't understand it. Maybe he also probably made it in relation to quantum mechanics. But the thing is, the explanation, the thing that you pointed out is it should match with human intuition. And we know now from all the experiments in quantum mechanics is the explanations never match the human intuition. So is it very essential that the explanation that the model comes up matches with your intuition? It could be something very bizarre, but still somehow logical. So it's just a comment. But the first part is, what's different between ensemble approaches and this shift?
Yeah, that's a very cool comment. I like it. Okay, so I think that's, like ensemble approaches or random forests, you can't really interpret them. I mean, like, you can interpret simple decision trees, like shallow, but if you go with big depth, then it's not really interpretable for human. So that's the reason for me to use just the linear models. I don't know, is it the core of the question, or did I?
That makes more sense, because maybe in these ensemble methods you have too simple and shallow, but in your method you're telling me that you can go for much more complicated architectures but still have some explainability.
Yeah, because there are two models basically always. Like you have the complex model like random forest, let's say, like big random forest or neural network, and the other model is just linear regression. And you have those two models are tied in this way that, so we have the input like image for the complex model, and the input for the simple model is just like ones and zeros, which correspond to specific superpixels in the image. And we do the linear regression, and we can interpret the linear model easily. So we just like they are tied all the time, and we explaining with the simple model the complex model.
Okay, you're just like focusing on the part of the data which was used to make decisions. So
So it's similar like with if we go with text and we have bag of words representation. So the input for the simple model is not bag of words, but it's also like the vector of zeros and ones.
Short one.
So how do you know how these models deal with the correlated features? For example, in the banking example, if you have age and years of experience, of working experience, how would which model, the model would pick which feature to explain? Because the features are correlated, you see. How do these models work with this kind of particularity?
Yeah, okay, that's an interesting question. I think in case of SHAP, because we are going, so in this general case, when we are going over all configurations, then those feature importance, I think that would be similar for both of them. Not sure how this approximation would work, but I think it would be similar.
Okay, thank you so much, Mateusz. Great round of applause, please.
Thanks a lot.